Okay, in this video, we're going to determine the current that flows through this 4.8 resistor by setting it up from a Thevenin analysis technique and using the Norton analysis technique. And obviously that would not be the quickest or the most efficient way to solve this problem. We thought it would be an interesting demonstration of the thought process that goes into analyzing something from the Thevenin or the Norton equivalent point of view. And before we do that, a reminder that the playlist for all the videos is at the website digital-university.org. Now here, with our relatively simple circuit, that before we set it up and use the Thevenin and the Norton technique, let's just solve it real quick, doing it the obvious way, using the loop analysis to determine the current flowing through this resistor. So let's say that here in this part of the circuit there is a loop current, we call it I1, flowing in a clockwise direction. And then here in this part of the circuit there's another loop current, I2, and we assume it's flowing in a clockwise direction. And if you've watched the previous videos, you know that when we solve for the magnitude of these loop currents, if we get a negative sign next to it, that means that our assumed direction was incorrect and we have to go back and change it. Okay, let's look at this part of the circuit. We're summing voltage drops in this direction. So here we're going from minus to plus. So that's plus 6 volts. I'll just write down 6. And then whenever we go across a resistor, the voltage drop is always plus to minus. So it's always then a minus sign here. Minus 6 times the amount of current flowing through it, I1. Then we have minus this resistor, 4.8. And the amount of current flowing through it is I1 minus I2. So that would be adding up all the voltage drops in this part of the circuit, and those have to sum to 0. And then in this part of the circuit, now we're going from plus to minus here, so that's minus 8 volts, or just write down minus 8. And the current that's going through here is minus 4 times I2, and then that goes to the 4.8 resistor, that's minus 4.8. Well, now the current is I2 minus I1. And those have to sum up to be 0. And we can simplify this top equation. It's just 10.8 times I1 minus 4.8 times I2 equals 6. And then from the bottom equation we have minus 4.8 times I1. And then we have plus 8.8 times I2 equals minus 8. So we have two things to solve for, I1 and I2, and we have two equations. So it should be all set. Let's see, for this one, let's take this over to this side of the equation. So we have 8.8 times I2 will equal, bringing this over here, that's now plus 4.8 I1 minus 8. Or we have, solving this for I2, we say that I2, we determine that to be 0.54 times I1 minus 0.9. So what we can do then is here, for I2, we can substitute that for the I2 here in the top equation, and that's going to be expressed entirely then in terms of I1. Get this in better focus. Here we just brought this over to this side of the equation, so we have this expression. Solve that for I2, we get this expression, and now we're going to substitute this right here. So we have 10.8 times I1 minus 4.8 times I2, which is this, 0.54 times I1 minus 0.9. That has to equal 6. So that's real simple to solve for I1, and I1, we rounded it upwards to 2 amps. Now I2, then actually that is 2/10 of an amp. Put the decimal point in. I2 is 0.54 times I1 times 2/10 of an amp minus this. So I2, we get minus 0.8. Having problems with decimal points today. Minus 0.873 amps. So the minus sign means that we have to go back up to here and change the direction of this. We could have easily have guessed that I2 is going to be going in this direction just by our simple circuit. But anyway, we have I2 and I1 both flow down across the resistor in a downward direction. So the amount of current going through 4.8, that resistor, equals this plus this, and that's just a little bit more than 1 amp, so we're just going to say it's very close. Just call it 1 amp. So that is then the amount of current going through the resistor. Now, let's analyze then this very same circuit, relatively simple one, only now we're going to use the Thevenin equivalent technique. So we don't need this. Okay, this is the resistor of interest. So this would be like the load resistor, and all the other parts of the circuit would be like the supply part. And what we do is, initially we remove this temporarily, and then we ask ourselves, what is the voltage across these two terminals? So the first step is determine the open circuit voltage. Our resistor of interest we just removed from the, temporarily removed from the circuit, so it's the open circuit voltage. And we have to figure out what is that. Well, we look now at what the current is once we remove that and just left this open. The equivalent circuit is going to be very simple. Here we have an 8 ohm or 8 volt battery in opposition to a 6 volt battery. So we have a net here of 2 volts going across 10 ohms. 2 volts, 10 ohms. So we would have a current here in this direction of 2/10 of an amp. So here we have 2/10 of an amp flowing across like this. So the voltage drop across here would be 2/10 times 4. That's 8/10 volts with the polarity plus, minus. Then over here it's 2/10 times 6. That's 1.2 volts with the polarity of plus, minus. So now what we can do is, let's just do a voltage summation here, a Kirchhoff voltage summation, and we'll do it, let's go in this direction. So we're going minus to plus, so that's plus 6 volts. If we're going minus to plus, that's plus 1.2 volts. So we add them together at 7.2 volts. So this has to go now plus to minus of 7.2 volts. So then we add them, it comes out to 0. So minus to plus, that's 6, minus to plus, that's 1.2, that's plus 7.2, plus to minus 7.2 sums out to 0. So the voltage drop across here is 7.2 volts with that polarity. So we know what the open circuit voltage is. 7.2 volts. Now, the next step is we want to determine what is the resistance of the circuit across these two terminals after we remove all of the voltage sources and all the current sources. So let's just redraw it. We don't need this anymore. We have 6 ohms and 4 ohms. And no voltage sources. So now we just have straight lines here, no voltage drop. And then we have this. 6 ohms and 4 ohms. And we're asking ourselves, what is the resistance of this circuit here measured across these two terminals? So imagine taking a potentiometer, and if we put it across these two terminals, what reading would we get? Well, the potentiometer puts out a small trickle of current, so we can imagine a small current going from here. Then some of it's going to get split up. It's going to go across the 4 ohm resistor and come back. Others of it will go across the 6 ohm resistor and come back. So if we're measuring the resistance of this circuit across these two terminals, then the 6 ohm and the 4 ohm resistors are in parallel, because this puts out a small current that gets split across these two resistors. So Rx is equal to 6 times 4 divided by 6 plus 4. That's how you find the parallel resistance, and that equals 2.4 ohms. And we can call this the Thevenin equivalent resistance or the Norton equivalent resistance. It's the same thing, so we just call it Rx. That's 2.4 ohms. So we know the open circuit voltage and we know Rx. That's 2.4 ohms. So now we have everything that we need to draw the Thevenin equivalent of that circuit. The voltage source is this, and this is in series with that voltage source. So we have 7.2 volts. This is in series. And this is 2.4 ohms. Okay, so there is the Thevenin equivalent of this circuit, only originally we had a resistor in here. That was 4.8 ohms. So let's put it in here. And the current going through here, of course, is going to be these two resistors added together. Divide the voltage by that. Well, this is 7.2, so 7.2 divided by 7.2 is 1 amp, just as we previously determined. Now, once we have the Thevenin equivalent, from that we can draw the Norton equivalent. Remember back in videos 8 and 9, we said that if we have a simple circuit like this, we can replace the voltage source with a current source. and this will be in parallel with that current source. And the magnitude of that current source is this voltage divided by that resistor. 7.2 divided by 2.4, that's 3. So we'd have a current source of 3 amps. This is in parallel with it. And then we have the rest of the circuit. So 3 amps. This is 2.4 ohms. Do a better job of keeping things in focus. And 4.8 ohms. Here we have this voltage source divided by that series, that resistor in series with it, or Rx value, and that is 7.2 divided by 2.4 is 3. There's a voltage source of 3 amps. This is in parallel with it now. Again, we demonstrated this back in videos 8 and 9, and then we have the rest of the circuit. So this should be the Norton equivalent of it, and the amount of current coming through here should be 1 amp. Well, let's do this. Let's just start right from scratch and determine the Norton equivalent of it and see if it comes out to be the same as this and what this current is here. So let's go back to the original circuit, and now right from square one we're going to determine its Norton equivalent. And again, what we do is, this is the resistor of interest. Temporarily remove it, and we ask ourselves, if we hooked up an ammeter across these two terminals, what reading would we get? The way we can determine that then is, imagine that this was just a conductor here, like this, and ask ourselves, what's the current going through it? So now we'll be a little bit smarter than what we were at the beginning of the video. We'd say, well, this puts 1 amp in this direction from that battery, and this puts out 2 amps from that battery. So these gives us then what we call the terminal short circuit current. Because to determine that, we moved our resistor and just put a conductor in there, and that is 3 amps. And determining that is our first step when we want to determine the Norton equivalent. And then the next step is, just like we did before a few moments ago, determine the resistance across these terminals after we remove all the voltage sources and all the current sources. So it's just like we did a few moments ago. We have this. Six and 4, and we ask ourselves, what's the resistance of this circuit across these two terminals, and we just determined that. That was 2.4 ohms, so we know Rx equals 2.4. So now we have all the information that we need to draw the Norton equivalent of our circuit. So we have 3 amps coming in for our supply. This now is in parallel with it. And then we have this. So these two, we get them in focus at the same time. This and this are entirely the same, but this had a 4.8 resistor in it. So we'll place that here, and we want to know the current going through it. So here we have 3 amps coming in, and it's going to be split across these two parallel resistors. So the amount of current through this resistor equals the amount of current that's being fed into these two parallel resistors, 3, times, then for the numerator we have the opposite resistor, 2.4 ohms, divided by these two added together, that's 7.2. And this times 3 is 7.2, so this equals 1 amp. So, which of course is what it's supposed to be. So again, just a demonstration of sort of the thinking process that goes into setting up either a Thevenin or Norton equivalent circuit. And again, obviously that wouldn't be the most efficient way to solve this kind of a problem. But we thought it was a good demonstration, again, of sort of the thinking process that has to go into a situation where you want to try to apply either a Norton equivalent circuit or a Thevenin equivalent circuit. So anyway, that's it for this video. In the next video, we're going to start discussing inductors and some of their basic properties. Then we'll carry the discussion further into capacitors and their properties. So come back and join us for those videos, and we'll try and solve some more problems.